Yeah, just for the benefit of people who are watching remotely, I've just put up on the blackboard this set of vector calculus identities that we shall use during the talk. So hopefully this works. Yeah. So what I want to talk about is this rather unusual effect that is just in the Nernst-Planck equations. So these are the equations that René was talking about at the start. So they're 100 years old, but nonetheless there still seems to be interesting things you can discover in them. And it's what happens if you have gradients of different salts which cross in the sense that they're diffusing at an angle to each other. And I've sort of illustrated this down here. So if you have, say, a sodium chloride source in green and a different salt here, they're spreading out by diffusion and the gradients overlap in the orange region. That generates the ion current shown in red. And I'll try and convince you that this is the case. So what I'm going to start off with is some experiments to explore this effect that were done by Ian Williams in Joe Keddy's group in the University of Surrey. And they were published earlier this year. So here's the experiments that Ian set up. And they're a kind of non-fluidic microfluidics device, if you like. So in skilled in making these channels where you have a microscope slide and a cover slip separated by double-sided sticky tape, as it were, to create channels where fluid can flow. So you make these things and you can introduce fluid and it flows in by capillary action. So we're interested in diffusiophoresis, so you can make a structure like this, for instance, in two stages. So one stage you fill this narrow side channel with a hydrogel plus an electrolyte. So you fill it with the hydrogel precursor and you cure it under UV light so it becomes a hydrogel. And then you can fill the main channel with essentially water plus colloid particles. And then as the salt diffuses out of the hydrogel, you generate a salt gradient and you can watch what happens to the colloid particles in this channel here. So it fills by capillary imbibition, but the flow fields disappear very quickly. So it's a static situation, and you're just seeing movement of the colloid particles by diffusiophoresis. So this was like a warm-up exercise, and to demonstrate the effect, we could build these things and measure diffusiophoresis in agreement with the theoretical expectations. Well, this is the thing that we actually wanted to look at that Ian constructed. And it's kind of two of these devices side by side, but operating at right angles. So there's two of these hydrogel salt sources, but they have different salts in them. Looked at various, I don't know why that's happened. Yeah. So looked at various salts, but I'm going to talk about sodium chloride on this side and potassium acetate on the top. So you make the hydrogels and then you allow this whole thing to be filled with essentially water plus negatively charged colloid particles, and you watch what happens to the colloid particles as the salts diffuse out and the gradients, so you have a gradient of potassium acetate this way, gradient of sodium chloride that way, as they meet and overlap. Trying to find where the mouse is. No, it's went. Should have practiced running the movies. Oh. This is annoying. Didn't have any idea why the movie's not playing when the. It's not happening on here either. If we can't do it, then I'll skip. That's
strange.
That's a bit weird, isn't it? So there's a yeah.
If it works there.
I
don't know what happened.
It's vanished. The screen has vanished.
Click here. There you go.
I think
that's quite weird.
I'll have to skip through it. So what you would have seen is the colloid particles are moving. And on the next one, there's use essentially particle imaging velocimetry, although there's no flow in here. And then the final is a control thing where you don't see the particles moving for no salt gradients. And this is the summary slide. So what you see the particles moving. This is nearly after about 2 minutes. So I emphasize there's no flow in here. The flow's all decayed away much faster than that. And we're looking at a region down here. So these salt gradients are starting to cross around here. So what you're seeing is diffusiophoresis up the sodium chloride gradient on this side. And essentially there's not much happening on the potassium acetate side because for minus 50 millivolt particles, that's diffusiophoretically neutral. But the key thing that happens is you see particles moving down in this corner where there are essentially no salt gradients. And this is what we termed action at a different distance diffusiophoresis. So you've got salt gradients around here, but they're causing particles to move down here. So what's happening is, as I'll explain, the salt gradients, when they meet, they generate an ion current which spreads throughout the solution. And associated with the ion current is an electric field by Ohm's law, similar to what René talked about. And that electric field causes electrophoresis of the particles. So in this case, the current is circulating that way, and these are negatively charged particles, so they tend to move in the opposite direction to the current. So the rest of the talk, to explain where this comes from, and it's actually in the Nernst-Planck equations, and it was all this time. And I think there's a very nice analogy to magnetostatics, which lets you understand how the ion current arises. So we'll start with the Nernst-Planck equations, which are René's basically introduced already. The only thing is I'm going to write these with a dimensionless electrostatic potential for the most part, which is the electrostatic potential multiplied by E over KT. So that's the starting point. The other thing is it's important that the diffusion coefficients of these ions are different. And here's the diffusion coefficients for sodium and chloride ions and for potassium and acetate ions. And as René mentioned, these are normally supplemented by the Poisson equation. We have no flow in our problem. But that has some implications. So that term on the right-hand side is the space charge. And my notation is fortunately almost exactly the same as René's. So let me introduce the Bjerrum length defined this way. And the Debye length, or 1 over the square of the Debye length, is proportional to what's known as the ionic strength. So I can rearrange this Poisson equation in stages. So let's pull out all the factors of E and KT onto this side and use this dimensionless electrostatic potential. Then we can write that in terms of the Bjerrum length. And now it's divided through by the ionic strength. And now this quantity is just the square of the Debye length. So these two equations are exactly equivalent. Except now we've explicitly recognized that we have the square of the Debye length multiplied by the Laplacian on the dimensionless electrostatic potential. Now the point is the Debye length is very, very short compared to our typical system size. What that means is this equation is essentially, you can think of it as a singular perturbation or a singular contribution to the equation set. So that in that sense, you'd expect boundary layers of thickness of the Debye length where the space charge is violated to order 1. And these are just the electrical double layers that surround everything that you dip into an electrolyte solution. But in the bulk regions away from the electrical double layers, this term is essentially lambda d over L squared, much, much less than 1, so we can, for all practical purposes, assume that the space charge vanishes. And that gives rise to Nernst-Planck equations in bulk regions where we assume local charge neutrality. So everything I'm going to tell you follows from these equations. And the way to think about them is that this electrostatic potential relaxes extremely fast, or the space charge, which is minuscule, develops on a time scale which is a Debye time. It's extremely short compared to the time scale on which the concentration fields themselves relax. So you can view the concentration fields as essentially frozen on the time scale that the electrostatic fields, electric fields develop. And that means we can use a quasi-static approximation. So roughly you can say, well, if the space charge is order lambda d squared over L squared times the bulk charge, and the bulk is relaxing on the time scale L squared over d, then you'd expect the space charge to relax on the time scale lambda d squared over d, which is this Debye time. There's a footnote which is the electrical double layers relax on an intermediate time scale, but that doesn't affect what I'm going to say. So here's that bunch of equations again. We can construct the ion current. It's just a weighted sum of the individual ion fluxes. And then if we take the conservation laws and we assume steady state on the time scale of the Debye time, we can impose charge neutrality, and we find that the ion current must be solenoidal. So it can't start and end anywhere. It has to go around in loops. It doesn't mean to say that it vanishes, and in fact it doesn't vanish in general. It vanishes in certain circumstances and in all the textbooks, but not in general. So to get going in this, I'm going to make a couple of definitions. So I'm writing the ion current as the weighted sum of the ion fluxes. And the ion fluxes are given by the Fickian diffusion term that René showed, plus the contribution from the electric field. So I'm going to write G for this weighted sum of the ion concentrations that derives from the Fickian diffusion. So there's a contribution to the ion current, which is minus the gradient of G. And another contribution which is proportional to the electric field, or the electrostatic potential gradient, which features essentially the conductivity. And then if you require that this ion current is divergenceless, that gives rise to an equation for the electrostatic potential, which essentially replaces the Poisson equation in this problem. And what I'm going to do is rewrite this lot. So I'll take this definition that I've had before and invert it to define the electric field in terms of the resistivity. So there's an Ohm's law bit, and there's a thing that's sometimes called a diffuse liquid junction potential. Now the thing is, being the gradient of a scalar, the curl, which is that one, curl of the electric field vanishes. So if you take the curl of this equation, you find that something rather neat falls out, which is what I call the ion current equations. And to get the term on the right-hand side here, so you have a curl of rho times I, and they want to take the curl of this thing. So we use this vector calculus result, which simplifies because the curl of the gradient bit vanishes. So you only end up with the curl of rho crossed with the curl of G. And I'm going to put it on the right-hand side here, so we flip those two around to change the sign. So now we've got essentially two equivalent pictures. One is what you do find in textbooks, where you work in terms of the potential, and there was this new view where you work in terms of the currents, so these current equations. So these are essentially quasi-static equations. They track the evolving ion concentration fields on the diffusion timescale, but these are essentially quasi-static. They reach steady state on the Debye timescale. And either set uniquely determines the ion current and the electrostatic potential. And that's just to remind you what these quantities are. So here's these ion current equations again, and if you stare at them and long enough, you think, oh, I've seen something like this before. This looks very like Ampere's law in magnetostatics. And the second one looks like Gauss's law. And its resemblance is even stronger because Ampere's law is usually written in terms of the magnetic field intensity, and Gauss's law in terms of the magnetic flux density, with a proportionality between them. So the only complicating feature in here is the resistivity of the solution can be spatially varying. Whereas in general in the textbooks, you don't tend to worry about that unless you're doing advanced electromagnetism. Also, if we write this source term here, then that is also divergence free, similar to the way that the steady state electrical current in Ampere's law is divergence free. It has to be the case because the divergence of a curl vanishes. We can also prove directly that the divergence of this cross product vanishes. That's the last of these vector calculus identities. So if you expand it, you end up with a curl of a gradient minus a curl of a gradient, and the curl of a gradient vanishes. So the real utility of this is you get some insights into where these ion currents are coming from. So they really say that the origin is where the salt gradients cross. And then what you should imagine is that that's like the electrical current in Ampere's law, so you can use the right-hand rule, for instance, if you get it the right way around, to say, well, okay, so there should be an ion current circulating around this region where the salt gradients cross, exactly like the way magnetic fields go around an electrical current source. And that's what drives this remote action at a distance diffusiophoresis. And here's the example I showed at the start. So these ion current lines are exactly analogous to the magnetic field lines around a small current loop, which is this circular or donut-shaped region where the gradients overlap. And you can estimate the strength here. So the dipole strength in the Nernst-Planck analog should be the scale as a square of the size of the salt sources, assuming there's essentially only one length scale in this. So the electric field should be proportional to K over E, because that sets the overall scale. This length scale squared, and it falls off as 1 over R cubed. And now we can also see why there's cases where you don't get ion currents. And there are generally two classes. One is in the binary electrolyte. Local charge neutrality means there's essentially only one concentration field. So that means the G scalar field and the conductivity are both essentially proportional to the same concentration field, and that means this cross product vanishes everywhere, even if the concentration field can have an arbitrary distribution. So that vanishes. The solution to the equations is I equals naught. I told you that they determine I uniquely. That means there's no ion current in the binary electrolyte. The other obvious case is if you happen to work in one dimension, then all these scalar fields are parallel to each other. The gradients are all parallel to each other. The cross product vanishes. Again, there's no ion current unless you inject a current with electrodes. So to see the effect, you need at least 3 ion species and at least 2 dimensions. On the other hand, it means that if you have at least 3 ion species and are working in at least 2 dimensions, it's almost inevitable that you'll have an ion current. So here's how it affects diffusiophoresis of suspended particles. So in a multi-component electrolyte, and I'm actually just going to write down the expressions for univalent ions, you have a contribution that comes from the overall gradient of the ions, which is chemiphoresis term. That generally causes a particle to climb up the gradient. And then you've got electrophoresis in the electric fields associated with the ion current, associated with the diffuse liquid junction potential. So I can take this decomposition that I had before and inject that into this expression for the diffusiophoretic speed of the particles, and you end up with three terms. A piece proportional to the gradient of the total salt concentration, a piece that's derived from local gradients, and this is the diffuse liquid junction potential, and the piece that derives whenever there's a circulating ion current. So generally these are all pointing in different directions, and you should add them together to get the resultant diffusiophoretic drift. Interesting, if there's places where there are no gradients, then only this ion current survives. So there are more videos, which I shall assume won't work, and I'll go straight to the answer here. So we are, Richard and Ian largely, solved the Nernst-Planck problem in this geometry where you have sodium chloride diffusing in from the right-hand side, potassium acetate diffusing in from the top side. This is the experiment. So you calculate the ion concentration profiles. You solve, in this case, you solve that inhomogeneous Poisson equation. You calculate the ion current, and then you calculate the effect on diffusiophoresis. So if you just include the local terms in diffusiophoresis, this is what you get. That you see there's a strong diffusiophoretic drift up the sodium chloride gradient. There's essentially nothing happening around potassium acetate because that's chosen to be diffusiophoretically neutral. But basically there's nothing happening down in this corner here. On the other hand, if you go to the full model, the correct model, include the ion current, you have a circulating ion current which goes that way around. And it correspondingly is an electric field down here. And because it's, the salt concentrations are low here, the resistivity is high, so the electric field's high down here as well. And that's what drives diffusiophoresis, or it's essentially just electrophoresis of the suspended colloid particles in this region, and that's why you see the particles moving down in this corner in the experiments. So it points in the right direction, the magnitude's about right, everything fits. It doesn't fit exactly because we don't exactly know what to use for the initial conditions, because there was some initial stirring as the cell was loaded, for instance. But it works. And so I'll finish there. How am I doing for time, Mike? Okay, good. So wherever you've got cross salt gradients in the Nernst-Planck equations in the book, you will get these ion currents, and they're solenoidal, they're circulating. So if there are 3 or more ion species and then 2 or more dimensions, and I like this, Howley's phrase, I think, is if it's not forbidden, it's mandatory. In other words, unless there's a strict reason for the ion current to vanish, there will be an ion current. So they follow the concentration fields on the Debye time, so that's very short time scale. And then the electric fields, some of which come from the local salt gradients, the diffuse liquid junction potential, some of which come from Ohm's law, just wherever there's an ion current. They're what drive diffusiophoresis of suspended particles, and essentially they mean that these cross gradients can reach out across the system and move particles at a distance. And this bit I really like is that those equations, they look very similar to Gauss's and Ampere's law in magnetostatics, so you can gain some insights into how these ion currents appear. That means they spread out like magnetic fields spread out from a current loop, and they're dipolar in far field. So you can prove that Essentially, it's because the ion current has to be solenoidal. And like I say, they propagate almost instantaneously. And we can delve into the realms of speculation here. So we have a way of signaling. So if we have an ion gradient on one side of the system, almost instantaneously it generates these ion currents in the electric fields that spread throughout the whole system. And we know of no evidence that it could be used for intercellular signaling, but it's there, and maybe the cells do use it. And that sums it up. And personally, I think that this was hiding in the Nernst-Planck equations for 100 years, and I think they're rather nice. So I'll stop there. Thank you very much.
Thanks very much, Patrick. Plenty of time for questions. Paddy first.
Patrick, it's very interesting talk. I'm curious about the third dimension. I mean,
Yeah.
experimentally, I'm guessing it's not straightforward, it's probably not impossible, but theoretically, what happens to the equations if you add the third dimension?
They stay the same. This is in 3 dimensions.
So you,
No. Something I didn't say actually. You don't get any more phenomena if you add more ions. 3 ion species is enough. If you have 4, then you change the G in a row, but you don't generate any new phenomena. And well, your question about 3 dimensions, one thing I think I've thought of is that you could imagine having dissolving salt crystals on a surface where the salt gradients then interfere with each other, and you generate an ion current that reaches out into the vault.
Consequences that we can take. So here you consider the bulk, but sometimes as soon as you have surface production, can be very heterogeneous. You have a lot of gradients stored.
Yeah.
Do you see that language immediately? Can you expand it immediately to this kind of
Where you have surface.
Conduction.
Yeah, right. Well, the E fields associated with the ion current will generate diffusio-osmosis or electro-osmosis at any interfaces. But it sounds like it's asking a slightly different question, which is that if you have conduction in the surface layer, which is a sort of Dukin number effect, we haven't thought about that at all, but there could be all sorts of interesting phenomena that arise from in more complicated situations. It's wide open. Oh, I see. I don't know. Yeah.
I do have a related question, which is when you switch from the kind of standard representation to this one which resembles Manxism, does that totally change the boundary conditions that you need to think about in that role?
No, it doesn't. So the boundary conditions are the same for both problems, which are typically that you want the ion current to vanish at a surface or to vanish at infinity. Right. So in the, let me just whiz back to this. We're okay for time, aren't we?
Yeah.
If we are okay for time, someone can ask me about the Biot-Savart law, but yeah. So these are the 2 equation sets, and they're essentially equivalent. So in this one, you want to specify the ion currents to vanish. So n dot I equals 0 at the surface, which amounts to specifying a gradient of phi. And this equation looks very similar to electrostatics in a medium with spatially varying dielectric permittivity, so you can prove uniqueness from that. This version here, it's a bit more explicit. You just have an I dot n equals naught on the surface, for instance, or I goes to 0, with the same boundary conditions. And to show that the solution here is unique, the only way I found is you can convert it back to this set by essentially integrating this first equation. You introduce phi as an integrating factor, you recover this equation, and then you have uniqueness from that. Yeah.
Any more questions for Patrick? David?
What is
Yeah. If there's a dual, it's the electrostatic potential. But it doesn't, like I was just showing. With magnetostatics, you have the B field and the H field. And in free space, they're just proportional to each other. And depending on what set of units you use, they're actually equal to each other. Whereas in these equations, you have the ion current and the resistivity times the ion current. Maybe I'll show this again.
That's, I mean, you said it was like the magnetostatics in a medium of spatially varying mu.
Yes, it is.
Which is what you do when you do boundary conditions and interfaces and things.
Yeah.
So that's not a completely alien situation.
Yeah.
Underground.
So an open question here is, if you have discontinuous media in this problem, what are the boundary conditions? We haven't done that. David? Yeah. Yeah. No. The way I think about it is that these things they're essentially quasi-static because they relax on this Debye time scale, which is very fast, very short.
Okay.
Yeah.
If there are no further questions, Patrick, we break for coffee.
Okay, thank you.